to this computer.
Cool.
Yeah, thank you, Miss Zoom lady. All right, so we'll try to record this because it'll be amazing, and we'll want to watch, our grandchildren want to watch this, I'm sure.
No pressure.
No pressure. Yeah, exactly. Anyway, let's see. Does anyone have any interesting announcements? I'm trying to get back into the groove of doing this every month, both, and I'm going to try doing this arrangement. I can bring it up another microphone, maybe, if that works for the room. They've got a webcam up in the top that I would love to tap into. I'll talk to Solomon, but we'll figure out. I did bring a webcam, so maybe I'll set that up while Michael is talking, and then you guys can look at the room. But anyway, we'll try to get people interacting, and probably we'll do breakout at the end like we've been doing on Zoom. For those of us playing in the room, maybe you guys want to join. I don't know how the audio is going to be joining in for the Zoom breakout later. Yeah, okay, that's fair. Again, we're making it up as we go, so thank you for bearing with us. All right, without further ado, because I don't have anything else interesting to say, I'm going to hand it over to Michael. I'm going to mute, and then I'm going to work on getting that camera set up. So why don't you introduce yourself, and you have the floor.
Awesome, thanks. Let me get my slides working. How does my audio sound? Can someone just let me know if it's good or bad? I see thumbs up.
Very loud in the room.
Oh, okay, it's not too loud, hopefully. All right. Can you see the slide deck right now?
Yes.
Actually, I don't.
Yes, we can.
I really don't actually want to. I don't want the navigator because I want to be able to like read chat and stuff during this. I really don't want to give like an hour-long lecture. I never really like those. I want this to be a little bit interactive with everyone. I'm just figuring out Zoom right now. It's a little too big. I'm okay with having like stuff like this just so I can see the Zoom meeting here. Or is it actually going to go? I'm just trying to figure out how to see chat right now. Show chat. Okay, so I can see chat. Like I said, I really don't want this to be like a lecture, so I'm trying to just make sure it's interactive for everyone. But yeah, let's begin. So the title of this is classifying bot IP addresses in Phoenix. My name's Michael. I'm the founder of Praxial.io. Just to double check, can I get a thumbs up? Can you see the slide deck right now? It should be all white. Perfect. Okay. So yeah, let's just go right into it. So my background professionally, I worked in software security. Praxial is a company that does bot detection just exclusively for Elixir applications. So the product competes with reCAPTCHA from Google, for example, or Cloudflare, which might sound a little bit odd, you know, competing against like billion-dollar companies. There's reasons, in my opinion, where you want some kind of specialty stuff with Elixir. So if you want to contact me about this talk, just feel free to send me an email. I'll put at the end of the slide deck as well. So before I describe kind of the problem for the talk today, could you raise your hand or do the Zoom thing? Has anyone here ever used the Radix try data structure before, either academically or professionally? I don't see any hands going up, so I'm going to say, sorry. Everyone's frozen on my end. Is my thing working right now? Okay, yeah, that's good. All right, so I got no one from that. Just out of curiosity, also, has anyone used persistent term? It's like an Erlang feature, kind of similar to ETS. Has anyone? Okay, I see one thumbs up. I see two thumbs up. That's excellent. All right. I've heard of Radix tries. All right, well, you're going to learn something new tonight. That's actually really excellent. Okay, cool. So the background for this problem is we're just going to talk about a simplified example for bot detection. So we're going to start with, we have a software engineer named Kat. She works for blackcatconcerttickets.com. And there's a web application there that's written in Elixir Phoenix. And she runs into this problem where bots, just people wrote a bot to buy concert tickets. They're buying all of the concert tickets before real people can. So the bot buys the concert ticket, resells it at a higher price. It's kind of called scalping. There's laws against it. It's kind of frowned upon. But if you've interacted with venues before, you're probably familiar with this. Right now, it's in the news a lot. Like you can't buy a PlayStation 5. In some cases, infant formula, because people are writing bots to buy up all this stuff. So And for our example, though, Kat notices this behavior and decides she wants to stop it. So she analyzes the traffic and realizes every single bot that is connecting to the website, to Black Cat concert tickets, is coming from the IP address range of a major cloud provider. And the reason that's a really good signal is because it's one of those things you can't spoof, like TLS signatures, HTTP headers, your user agent, all of those are set by the client, but just because of the way TCP works, you can't spoof that value. So it's actually a pretty useful tell. Naturally, this is a simplified example. Real world bot detection is more complicated, but let's just use this as kind of our discussion problem for tonight. So pretty straightforward. The bots are buying up the concert tickets before the humans, and that's what Kat is working on. So are there any questions about this before I continue? This is just kind of like the description of what we're going to be solving today. I don't see anything in chat or from the room, so let's continue. Okay, so naturally we're in Elixir and Phoenix, so let's write a plug that will stop these rented cloud servers from buying all of the concert tickets. So for this example, we're going to say there's about 1 million IP prefixes from this cloud provider mixed against like IPv4 and IPv6. We want to put all of those into some kind of data structure in memory. Request comes in, like your con.remote IP, compare it against this list. It won't actually be a list. I'll show you why a list would actually be a very poor choice here, but we want to very quickly compare that and then determine if we should allow the request through or halt it so that they can't buy the concert tickets. So let's kind of look at the problem. We're just going to do problem 1 first, which is how do you quickly match an incoming IP address against the data structure? The second problem we'll talk about is how do you have all these processes accessing this in a quick period of time? That's later. So for an IP prefix, which is what we're going to be working with, that's what's published by the major cloud providers. So the 35140.0, that's an IPv4. The 2600, that's IPv6. Like we said, Kat has 1 million of these, wants to represent them in some way that you can very quickly match them in an efficient way. So the first kind of bad idea here is trying to expand this range into individual IP addresses. So for IPv4, this is a /22 in CIDR notation. That just means that this represents an address range of about 1,000 IP addresses, which is sort of in the realm of what you could do in like a set, an Elixir or a map or whatever. The problem is once you get into IPv6, the number of IP addresses you'd be working with is way too large to represent in memory. So you can't just use a set, basically, is the summary of this. You're going to run out of memory. So to think about this problem, think about just kind of information encoding in general. So let's say you're in Elixir and you want to represent integers from 1 to 1 million. You wouldn't literally put a list of 1 to 1 million. That's just wasting memory. You could just represent it as a range or just compare, like, is it greater than or less than, you really only need the 2 integers. And that kind of idea of information encoding hints at the solution here, where all of the information you need to solve this is actually in the /22. So we know that there's about 1,000, IP addresses in this range. We just need a way to represent, it's probably a string. Like think of it as coming down from JSON from the cloud provider as a string. How do you represent that in Elixir in a way where you can do these comparisons quickly? Turns out there's actually a really nice library called PFX that does this for you. It'll actually parse like a string coming from JSON. You can see the 35140 there. And it's just a bit string in Elixir with a length of 32. Same story with IPv4. Naturally, the difference is the max length of an IPv6 address is 128 bits. And when I say bits here, I literally mean like binary. Like imagine 00010 for a length of either 32 or 128. That's how IP addresses are represented in networking things. So now you have this kind of next iteration where, okay, let's store all the IP prefixes in like a normal Elixir list. And then when a con remote IP comes in, we just compare it against this IP prefix, this IP prefix. It's fast. you don't have to represent the billion IPv6 addresses or whatever. The problem is, as your number of IP prefixes increases, this is an O to the N algorithm. So it's going to linearly increase and your performance is not going to be very good. This is kind of a classic example because lists and Elixir, if you want to determine if, some item is an element of a list, you have to iterate through the entire list to determine that. And that's where this algorithmic complexity comes from. So now that we've kind of talked about the problem, I want to introduce the Radix trie, starting with this diagram. So consider you have some integers that you represented in binary. So the first one would just be 0, that'd be 0, 0, 0, 0. There's 1, there's 2, and then we go up to 8 here. Notice that they're all the exact same length. So it's possible to represent them in this trie where if you want to determine if an integer is in the data structure, you don't have to have like every single one represented. You can compress it a little bit and then navigate down the trie to determine if an item is in it. So to get more concrete example of that, let's say you want to determine if the number 8, which is 1, 0, 0, 0 in binary, you want to determine if that's in this trie. If you had a list, you'd have to enumerate through every single item in the list. That's where you get that complexity problem. With the trie, you look at bit 0, and bit 0 here means all the way to the left. So there's only one number where the bit 0 is 1, that's 8. You just immediately go to the right from the top node, and then you found it. So it's much more efficient compared to that list. Similar if you were to try to find like if 0 was in it, you'd have to go down a few, but you can see how it's not, you're not going to explode with ON. You actually get a much more efficient lookup. So there's also a library for representing Radix tries in Elixir, kind of designed for IP addresses. It's a similar story here, where if you want to check if an IP address exists in the trie, you look at the first bit, where this is IPv4, so it's a 32-bit length, bit number 1, and then you can immediately determine if that 1 is in the trie. We just got a comment in the chat, so I'm going to read that really quickly. As a network engineer and not really a coder, that makes me happy. Thank you. That's great to hear. Yeah, you don't really see too much of this typically in certain parts of software development. So it's cool to kind of like show it in Elixir. Typically you're in C when you're working with this stuff, it feels like. So if you wanted to represent an IP trie in Elixir, this is what it would look like. It's basically just a map, and then your kind of pointers are just a map in Elixir. So you might be wondering about what the performance implication of this is. So this is for 10,000 prefixes. It's, you're still pretty fast, but you can see that you're using just entirely different units of time. It's like millisecond versus microsecond to determine it here. I hope you can see it in the room, but if you can't, it's, the trie lookup is just much faster. And then here's the numbers if you increase it to 100,000. And then finally, when we're at 1 million prefixes, the lookup time is still like 0.00082. Compared to the list lookup that I showed you earlier, there's now a noticeable delay. And this is just for the lookup. That when you have a real world application, there's more of a delay. So this is just kind of a good example of where you'd want to be using a trie. So that kind of concludes problem part 1. I'm just going to pause for a second. I'd like to take questions or kind of hear what your thoughts on it. So I'll just pause for a minute. I don't know if there's like a microphone in the room or anything.
All right, not seeing any questions over here.
All good? All right, cool. So yeah, we can just continue on to the next part. So now that we have this data structure, 1 million prefixes is a lot. In kind of a real world thing, I've dealt with cloud providers like this. Typically like 60,000 is the larger one I've seen. I just like the 1 million example because it demonstrates this algorithm complexity really well. So let's just say that we're dealing with 1 million prefixes here, and that's about 28 megabytes in memory if you represent that. So now this brings us to kind of the Elixir, really Elixir specific part, where you have this large data structure. It's kind of like a custom thing. It's this special kind of map, and you need all of these processes to access it. So the first place that you might be reaching here is for a gen server, which is a really bad idea. And the reason for that is, you typically would use a gen server to maintain some kind of global state in your application. But you've just introduced this bottleneck where, okay, we want to determine if IP0, let's say that comes in, and we want to determine, is that a cloud IP or not? That's fast enough. The problem is, let's say you have 100 clients connecting at the exact same time. Now there's this sequential queue of incoming IP addresses, and the gen server has to process it one by one, meaning like, let's say there's a 1 ms delay inside the gen server. That's going to be, 1 ms, 2, 3, 4, all the way backed up to 100. And you're going to see that, also not counting the increase in memory from all of these messages getting backed up. So you've just introduced this bottleneck in your entire application if you do this. And this is such a common pattern, introducing this bottleneck, that the Elixir Getting Started guide mentions it and then uses it to introduce ETS from Erlang. So that may be the next place you reach in this example problem, but it's also not really a good fit here. And let me show you why. So imagine you've put this IP try in ETS in just like a normal set. So you have your key, which would just be like an atom, and then the value in the key value store is the 28 megabyte try. So you have a process ID, PID 0. It wants to get the IP try. It doesn't have a native data type for that. So the whole thing is being copied back to your PID. So you're actually going to see that increase in memory when you run observer. So now every time a process wants to get it out of ETS, you're going to see that memory copy. So you might think, like, when would you use ETS? This seems kind of bad. If the thing you're accessing is really small, you can take this hit on the memory copy because it won't really affect it. It's just, okay, the process gets it, does its work, and then it gets garbage collected. When you're dealing with a larger data structure here, it's kind of like the worst case scenario because you're going to blow up your memory consumption really quickly. And the thing is, you can have 28 megabytes of data in ETS, for example, in like a set, and then you can do a lookup into ETS. That is still very fast. The problem is ETS doesn't have a lookup radix try, API implemented. So that's why all of these processes have to do this memory copy. So gen server didn't work, ETS didn't work. It might feel like we're dead in the water, but let's just restate the current problem really quickly. We have a big data structure. It's 28 megabytes. There's a lot of processes that have to access it quickly. And the reason for that is when you have 100 clients connecting to all purchase concert tickets at the same time, all of those are spinning up processes, and then they all have to connect to get this radix try. And that's the reason that you would see like the memory blow up with ETS or the gen server bottleneck. It's also worth noting, though, that IP try does not change very much. So the design for the cat would have here is just on startup, do HTTP requests or check your file system, build this radix try data structure, and then it's pretty much static for the rest of the application's running time. So now we're going to introduce a persistent term, which comes with a warning label, which is kind of cool, saying don't use this as a replacement for ETS. Make sure you really understand your problem first. But it's kind of perfect for this use case where it's highly optimized for reading at the expense of writing or updating. So when you read from persistent term, there's no longer this memory copy, but the reason for that is you're sharing kind of like the address of it with all of your processes. So if you were to update it, that would trigger this global garbage collection that's going to degrade the state of the entire system. So that's why there's this warning label in the Erlang documentation. It's because don't use this as an ETS replacement, because if you do an update and then you have 1,000 processes holding that reference to the data structure, all of them get a garbage collection, and that will degrade the state of your system. But we are not affected by that in our case, so it's kind of like the perfect thing. So I implemented this with ETS, as you can see here. And this was only with 20 processes, which is pretty light. And you can see there's a massive memory spike up to 3,000 megabytes. If I increased it to 100 processes, the whole thing would crash because it would just run out of memory. compare that to persistent term, it does plateau around 300. I could have optimized it a little better, but the summary is once the radix trie is actually built, the different processes accessing it don't increase the memory at all. It stays completely plateaued. So that's why you would use persistent term here. So to summarize now, CAT implements the implementation described here, the 1 million IP prefixes in the IP trie using persistent term. When a request comes in, it's checked using a plug. And if it matches a rented cloud server, which is like, if you, for example, get like a login attempt from a rented cloud server in your real, let's say you manage a web app for your day job, there's a 99% chance that's someone rented a server and is just brute forcing your credentials and you don't want to serve that traffic. It's kind of similar story here. You just want to drop it. It's probably a bot, and then the real people can buy concert tickets. And naturally, this is a simplified example because this talk is really not about bot detection. I'm happy to chat more about it because I do that professionally now. It's really more about how you would solve a problem like this, in Elixir using the things that are available for you. So the conclusions from this talk: think about the problem you have and pick the correct data structure. Gen servers can become a bottleneck. ETS will copy non-binary format data to the calling process. So watch out for that. If you see kind of jagged memory usage in your observer or whatever, it could be because of that. And then finally, if your data isn't updated frequently, but it's being read a lot, and you have like a big data structure that needs to be read a lot, persistent term is a really great tool to reach for. It's also worth notice, if there's any like really smart Erlang people on this call, it may be possible to improve on this solution by using ordered set in ETS, where you take all of the IP prefixes and you would like rank them, based on the order of them. Essentially, you'd sort them, then put them in ETS, and then you could kind of navigate over ETS and do a call in. And the benefit of what's described on this mailing list is that you would actually get update in the data structure without, like what we described here, it's kind of a read only. But if you were to get this implemented, you could do like updates as your application is running without having to deal with the degradation. So that's the conclusion of the talk. Thank you all for listening. I appreciate it. It's based on a blog post if you want to read more or run the code. So I'm going to go read chat really quickly and also take any questions that anyone has. So we have one in chat. You can override the default inspect function in Elixir. It uses persistent term to store that new default. That makes sense. Yeah, I actually didn't know that. That's really interesting. Thank you.
Another thing to look at, TZ, the library that replaces TZ data, has a different way of solving the same problem. Like it's
interesting.
Because it's the time zone database is a very slow updating, but it's a lot of parsing that needs to be done when you download the new database. And so what it does is it uses Elixir macros to just compile it into a function every time it does the update. But because it's in Elixir, you can live do that every time it updates, even in a running application. So it just has like a macro and then like a compile function that calls the macro. That does the same thing. It solves the same problem.
Interesting.
Would that work? I mean, how well does that scale though?
I mean, you use time zone databases in your Elixir projects.
No, okay, right. Well, I mean, there are not millions of time zones. I'm just thinking the IP problem is a bigger problem potentially, right?
Yeah, the data structure is probably smaller for time zones, but time zones are, I know at least with TZ, it's calculating ahead of time, like the next 5 years worth of time zone changes, daylight savings ending, starting, etc., for every time zone in the world. I don't know how big that is compared to the 28 megabytes here. I suspect that it's smaller, but I don't know how much smaller.
So Brett, if you think about this, think about the approach that was just described. This is getting into the other talk I might have done that you chose not to have me do. If you have a macro that writes a function that is going to look up the IP address of the time zone or whatever it is, you can build the data structure as a literal that's local to the function, And when you call the function, it just looks through the data structure as a local piece of memory. So it could be, so you just now have a function that returns whatever, and it can be called from anywhere. So I would think it would scale quite nicely.
Yeah, I've seen that. I think that's how Discord did it with their fast global library, and persistent term I think came after it. But yeah, it's like that's the exact idea that I'm trying to get at here. That's correct.
I suspect if you did it with the macro that wrote a function, it's probably a little bit easier to do the updates, because now you're kind of doing a using the software updating capabilities of the Beam, which is probably going to be faster than if you have to have a persistent term cause a massive number of garbage collections.
Interesting. Yeah, I don't know the exact details, but that is definitely in the same ballpark as this.
Yeah, I mean, I don't know how the Beam does it, but when I did work with this kind of stuff in C, we were able to update a function in microseconds, because the functions that were being called were it's actually a table of addresses. So when you call the function, you jump through a table. So it's just an indirect address and jump. And if you wanted to change the function, you just patch the table.
Yeah, that makes
essentially
sense.
no time.
Yeah, that is cool. Okay, there's another thing in chat from Jeffrey. Persistent term is one of the major keys to the solution. Aside from it sucking for things that are updated often, are there downsides for using it? I know it's sort of newer, but for example, is there a reason we don't use it for application config? I've actually read the source code of, I forget what application performance monitoring it was, but I've read like the source code of an agent where they were using persistent term exactly for that. So it may actually be a great use case for that. So that's a great question and comment. Another thing from chat. In what cases the read-only structure you mentioned could change? And if it changes, is the side effect get rid of the clients that are in use? So I think what this question is trying to get at is, if the system was running and like a change to this happened, how would that affect everything? I did actually test that. I just didn't put the graphs in. Essentially, the global garbage collection causes all of these processes now have to refetch it. So you'll see a spike in memory, and then the overall response time of your whole application can go down. So that's like the reason for the warning label. When you go to the persistent term, there's like a red thing that's like, don't use this as an ETS replacement. Watch out for that.
But I would expect the hit from all that to be relatively short term.
Yeah, I think it depends on how many processes currently are holding like the reference to the persistent term. So if it's only a few, it really won't be that bad. But if you have thousands and thousands of processes, apparently the Erlang like docs are very adamant about being careful of that kind of. And I think I found a case where someone got bit by it in production as well.
Yeah, I would expect what would happen is you'd have a big performance hit where everything slowed down for a second or 5 seconds or a minute or something. Then everything was normal because everybody had already updated.
Makes sense. Okay, more in chat. Application config uses ETS lookup since it's a known data structure for most configs. It's probably optimized the way Michael said. I don't know the detail, but yeah, essentially, yeah, like for application configs, the speed is really fast. So you're not going to see too much of, you're not going to see an order of magnitude difference between persistent term and ETS lookup unless your application configs are in the megabytes, I suppose, which is a little unusual.
Anybody else have questions they'd like to ask Michael? All right. Well, thank you very much. That was pretty cool.
Yeah, thank you for having me.
Real world application of our computer science theory there, and using Erlang once again, which is good. Dig deep and take the benefits that we get for free, which is pretty nice. All right, so I'm going to stop the recording.